In this week's headlines, I present to you a quantum tornado that supposedly has something to do with black holes. Do they just put the word quantum in front of everything now? No, it's actually a pretty good description. Let's have a look. The headlines are about a new experiment at the University of Nottingham. They used superfluid helium at just a few degrees above absolute zero to simulate quantum effects nearby a rotating black hole. Is this just their idea of fun? Probably, but they had another reason. It's the best way we know to find out how quantum physics works near a real black hole. This quantum simulation of a black hole might sound similar to the infamous headlines of last year about a wormhole in a quantum computer, but it's very different. The wormhole stuff wasn't just a simulation, it was a simulation of a mathematical duality. For this, you first have to reformulate the mathematics and then you simulate that. But because of this mathematical reformulation, the simulation itself doesn't physically resemble the real thing. So there wasn't anything like a wormhole in the quantum computer. A direct simulation, on the other hand, is like this wind tunnel to test aircraft. It's a physical model of the real thing, but one that can more easily be controlled and measured. The new experiment now is a direct simulation, much like the wind tunnel. Of course, they don't create a real black hole either. That'd require even more pressure than nuclear fusion. Instead, they create what's called an acoustic black hole from which sound can't escape. The flow of the superfluid simulates the curved space-time around the black hole, and then they want to measure what the sound does. Though I must add that what physicists mean by sound isn't exactly Beethoven's symphonies. They just mean there are perturbations traveling in the medium like sound travels in air. And since they use a superfluid, the sound has quantum effects, so it's sound quanta that they're after. This analogy between superfluids and black holes isn't just words. The equations are actually the same. This relation is known as analog gravity. The equations are the same provided the medium has a suitable behavior. For one, it needs to be a superfluid, and it also needs to flow in a specific way. That's why they need the quantum tornado. Superfluids have been used before to simulate black holes. The most famous work is that by Jeff Steinhauer at Technion in Israel. In 2015, Steinhauer used a condensate of supercooled atoms to simulate a black hole horizon. In this experiment, Steinhauer wanted to test whether black holes emit radiation, as Stephen Hawking predicted. Hawking made this prediction in 1972. He calculated that black holes must have a temperature that's inversely proportional to their mass, and that means they emit light and other particles. Basically, Hawking said that black holes aren't entirely black. Unfortunately, the temperature of real astrophysical black holes is way too small to be measurable. But if Hawking's calculation was right, then the superfluid analogy of black holes should radiate too, because the maths is the same. And Steinhauer found that his black hole simulation indeed confirmed Hawking's prediction. However, Steinhauer's experiment had a big shortcoming. His black hole simulation didn't rotate. In the real world, black holes rotate. That's just because when matter collapses to a black hole, it's very unlikely to not have any angular momentum.
Now you know. That's cool. You can do a black hole simulation.